Hey there, Chem Squad. In today's class, we're going to look at how to do a type 3 equilibrium problem. So in a type 3, you are given at least one concentration that is at equilibrium. Okay. Now, there's another kind of situation here too. In this particular question, you're also given initial conditions. Okay, so if we look at the sample question reads 0.02 molarity of N2 and 0.02 molarity of O2 are placed in a container and heated. Okay, so both of these concentrations that were given are actually called initial concentrations because they're describing what happens at the beginning. Now, at equilibrium, you have 0.0050 molarity of NO2 present. Okay, so what they want to know is what is the molarity of each reagent at equilibrium and what is the KEQ value. So when you see a question like this that talks about initial and equilibrium, you're going to need something called an ICE table in order to complete the question. So let's just look at the reaction first. So I've written out the reaction. So you have N2 plus O2 to give you NO2. One of the first things that we always do is to make sure that it's balanced. So this side has 2 nitrogens, this side has 1. So I'm going to put in a coefficient 2 in front of the NO2. Because I do that, I double the amount of oxygen to 4. So I have to put a 2 on the reactant side to make 4 oxygens here, and a coefficient 1 in front of the N2. So what we actually have here, everything that we see on this side, okay, the reactant side, if we were to draw it out so that it's a little bit more visual, okay, so let's say you put in these substances into a beaker, or sorry, not beaker, but Erlenmeyer flask. You're going to have N2 and O2 in the reaction vessel. And because this is the initial, the concentrations that you have are all initial concentrations. So N2 initially starts off as 0.020 molarity. O2 was also given to you as 0.02 molarity as well. Okay. Now, the question says once you heat it, so we'll add heat, it will now begin the reaction and start creating NO2. So we're going to seal up the flask with a stopper. Okay, so now we have a closed system. And we still have our nitrogen and oxygen molecules, okay, in the container. But because the reaction has been running, you also create NO2 molecules now. Okay, and because this is a reversible reaction at equilibrium, okay, the only concentration that we are given is the concentration of NO2 at equilibrium, and that was 0.0050 molarity. But the problem is, we don't know the concentrations of nitrogen and oxygen at equilibrium because some of this material has been used up. Okay, because the initial amounts that you have, some of it has been used up to create NO2. So we're not sure exactly how much how much N2 and O2 are left over. So that's why we actually need a special table to help us figure out how much is left over. So let me show you the steps first. Okay. step 1 is to always balance your chemical reaction, which we did. Step 2, check for molarity. Okay, so what I mean is everything in molarities? Okay, because sometimes I give you moles, and if it's in moles, you have to convert it to molarity. So everything that we are given in the question is actually in molarities already, so we don't need to convert. So this is done. So now you're on to step 3. Now we have at least one initial concentration given. Okay. So we actually have more than one. We have both initial concentrations given, okay, but if you have at least one given, you have to set up an ice table. Okay. Now, the key to a type 3 is that you're also given at least one equilibrium concentration. Okay. So because you're given at least one equilibrium concentration, this sets it up as a type 3 reaction. Okay. You'll realize later on the difference between the type 3s and the type 4 and 5s. Okay, and it's basically this given equilibrium concentration. Okay. Now, because we have an initial concentration given, we set up something called an ice table. And once we fill in all the appropriate information of an ice table, we then use that information to set up a KEQ expression and solve for KEQ. So let's do that. So in order to set up an ice table, okay, I'm going to need to write out what kind of reactants I have. Okay, so I have 1 N2, we have 2 O2, and we have 2 NO2. Okay, because we have 3 reactants, three substances, we're going to have 3 columns. So the size of the ice table depends on how many substances are in the reaction. Now I'm making this a little bit bigger than I normally would, mostly because we have to do some calculations inside this table. Okay, so one of the first things that we do is we put in the word ice. Okay, each of them will be its own row, like that. Okay, so the I stands for initial concentration. Okay, the C stands for change in concentration. Okay, and the E stands for equilibrium concentration. Okay, so together it spells out ice. Okay, now at the very top is your reaction. Okay, so some people might even call it a rice table. Okay, but most people call it an ice table. So there are certain components of this ice table that we can fill in already. Okay, for example, we know what the initial concentrations of our 2 reactants are, okay, because they were given. It's 0.020 molarity. Okay, so we fill it out the way that it was given to us in the question. Okay, the other substance that we also are given from the question is the equilibrium concentration of NO2, which is 0.0050 molarity. Okay, so everything that I have in black here is something that we are given from the question. Okay. Now, what I'm about to write next is the stuff that we interpret. So, for example, initially, we do not have any NO2. So the concentration of NO2 is 0 at the beginning, at the start. Okay. Now, once equilibrium begins, we are going to be using up the reactants. Okay. So I'm going to put a negative sign in front of the two reactant columns because we're going to use up N2 and O2. We're also going to put a positive sign in the NO2 column, okay, because we're going to create products. We're going to gain products. So the negative signs means that we're using up reactants. The positive signs means that we're creating products. Okay. Now, to fill in the rest of the table, okay, we're going to have to use what we're given. So one of the things about this is, in a type 3 reaction, you are given the equilibrium concentration of at least one of your substances. Okay. We set up an ice table because we're giving initial concentrations. But what makes this a type 3 is this number here. Because we're given the equilibrium concentration of one substance, we can figure out all the other boxes. Okay? So this is what you have to ask yourself. If we just look at NO2, NO2 started with 0 molarity, but then at equilibrium, it has 0.0050 molarity. So how much did it change by? Well, the change has to be the same number. Okay. 0 plus 0.0050 will give us 0.0050 at equilibrium. So this is the amount of change. That NO2 has to go through in order to get the equilibrium concentration. Okay. Now, for the other boxes here, okay, we're going to have to use a little bit of stoich or ratios. Now, because we have our coefficients, okay, from our balanced equation, it's a 1 to 2 to 2 ratio. Okay, so if we just look at NO2 with O2, we can see that they're the same number. It's 2 to 2, or basically reduced down to 1 to 1. This amount of change is affected by the coefficients. Okay, so because this is the same ratio, it's going to change by the same amount. Okay, so this is a 1 to 1 ratio between O2 and NO2. Okay, now to figure out the value for N2, we look at the ratio between N2 and O2. It's a 1 to 2 ratio, meaning that you have twice the amount of O2 as you do N2. So that a way of looking at it is, you will always have half the amount of change for N2 here. So if this is a 1 to 2 ratio now, okay, we're going to have to take 0.005 and divide by 2. Okay, or the other way of looking at it is to multiply by 1/2, okay, which is the same thing as dividing by 2. So in the end, this number here is going to be half of 0.0050. So it should be 0.0025 molarity, okay, because it's a 1:2 ratio. Okay, so in order to get this number, you had to divide by 2 or multiply by 1/2. Okay, so the amount of change is always related to stoichiometry, okay, to the coefficients in front of every substance. So once we have how much these substances are changing by, we actually now calculate the amount of change that's given. Okay, so now we're going to read the first two columns from top to bottom. So if you start with 0.020 molarity of N2 and it changes by 0.0025, then it's just 0.020 minus 0.0025. So you subtract, and when you subtract those two numbers, you get 0.175 molarity. Okay, so remember, when you're reading it down like this, you're subtracting. Okay, so we can do the same thing for oxygen. We take the initial amount, 0.020, and we subtract 0.0050. Okay, that's going to give us 0.015 molarity. Okay, so this is the way that we have to look at the ICE table. Okay, because once we've completed the ICE table, it gives us a bunch of useful information. Okay, so it gives us the concentration of N2 at equilibrium. It gives us the concentration of O2 at equilibrium. And of course, we have the concentration of NO2 at equilibrium. So using these three values, we can now solve for KEQ. Okay, so we've answered one part of our question. We've answered the part in terms of what are the concentrations of all of our substances at equilibrium. Okay, there are these three numbers. The second part was to solve for KEQ, find the equilibrium constant. So if we're following our steps, we write out our equilibrium expression. So it's always products. Oops. It's products which is NO2, okay. The coefficient 2 becomes the exponent 2 over my two reactants. So N2 times the concentration of O2. And O2 has an exponent 2. Okay, so that's my equilibrium expression. So now I substitute all the values. So NO2 is basically 0.0050 molarity squared over 0.0175 molarity times 0.015 molarity squared. Okay, so this is our substitution step. Once we have our values substituted, we basically now just solve. So in the end, I'll give you the in-between step here. If we solve for the numerator, it's 2.5 times 10 to the negative 5. When we look at everything in the denominator, it's 3.937 times 10 to the negative 6. Okay. We make that final calculation, and KQ now ends up being 6.35. Okay. So since KQ is less than 1, oops, sorry, not less than 1. So, since KQ is greater than 1, okay, because 6.35 is greater than 1, the product side, or the products, are favored at equilibrium. Okay. Which basically means that at equilibrium, you're expecting there to be more products than reactants, okay, at equilibrium. So that is the answer for our type 3. Okay. So again, just to review, balance the equation, check for molarity, set up the ICE table, fill in all the information in the ICE table, set up the KEQ expression, and then solve for KEQ. So if this all seems overwhelming, that's natural, okay, because for most of you this is probably the first time that you had to use an ICE table. Okay, so it'll probably take you a bit of time and practice to get the hang of it. But once you do, a type 3 is actually a pretty straightforward type of question. Once you're able to fill in the ICE table properly, you should be able to do math to solve for your KEQs and your equilibrium concentrations. So what I want you to do now is to try this one on your own. Okay. So for practice, I want you to look at this particular question and figure out what the KEQ is. Now, I've given you the answer here, okay, so that you can check on your own to see if you're getting it right. What I'll probably end up doing is I'll post a solution for this particular question with the completed ICE table. But I do want you to try this, and if you have any questions, just feel free to email or message me. That's all I have for today. See you guys soon.